Hi, everyone. Okay, maybe just drop me a comment or so to see if you guys can hear me and see me clearly. Okay. Good evening. I am Julianne, and I'm very excited to welcome all of you to our first ever Nerve Online event. Yeah, so maybe just a thumbs up or so I can see that people are hearing me. But yes, so I wish we were all coming together under better circumstances. Okay, great. People can hear me. Cool. I must say, this is indeed a very strange and uncertain time in the world right now. But I hope everyone is keeping well and keeping safe. And we decided that lockdown is no reason for us to not all come together still. And we thought this is as good a time as any to finally launch Nerve Online. So on that note, I'm going to give a quick introduction of our group, and then we will get started. Okay. So our neural engineering research venture, or NERV, was established in 2017 by Prof. Dawie van der Heever and myself. Dawie is currently the head of the biomedical engineering department at Stellenbosch University. Some of his favorite things to talk about are free will and consciousness, and it is his love for neuroscience that started this whole nerve journey. I was one of Davie's master students when we started out with this research venture initially. At first, it was just us talking in his office about big ideas and brain stuff. But then we decided we wanted to create a more official platform where everyone can celebrate neuroscience and where like-minded people like all of us can come together and discuss this. So in 2018, Siobhan also joined our department and our research group, and she soon became a very integral facilitator for our discussion group. Siobhan and I bonded over our shared interest and our research in human decision-making. So yeah, I must say she's also been a monumental driving force behind launching Nerve Online. So thank you so much, Siobhan, for facilitating this. Yes, we are very excited to launch this platform where everyone who is interested in the brain can have open access to neuroscience research and just discuss everything together here. So yes, our aim is to bring neuroscience to Africa and to everyone all around the world. So I'm incredibly excited to welcome you all here tonight, and also to to show you some of our global engagement. So tonight it seems like we have people joining from South Africa, from Belgium, the Netherlands, Greece, Italy, the Congo also. I hope I'm not missing anyone here. And our engagement, as you can see on the map on the screen, we've engaged with people from Denmark, from Greece, SA, the UK, the Netherlands, the US, Kenya, Ghana, Italy, and the DRC. So this is all very exciting. So I'm now going to hand over to Siobhan, who will explain some house rules to everyone and who will then introduce our first ever NERV speaker.
Good evening, everyone. It's really awesome that everyone could join us tonight. Just going forward, if we can all just be mindful of the diverse range of views that we have here tonight. And please, this is, even though we are online and not in the same room, we'd like to facilitate discussions as best as we can. There's a ask a question feature. Please use this to post your questions and then also vote on your favorite questions. Once Chris has finished speaking, we will invite you to ask your questions live. The most popular questions will be asked first. If you aren't too confident or you're experiencing some difficulties and are a bit nervous to come online and ask your question live, don't stress at all. Just add "please ask" in your question and we will ask for you. And then do not fret if your connection is slow. You can adjust the resolution in the bottom right-hand corner. Then, without further ado, I'd like to invite Chris to the stage. Chris is currently doing his PhD in computational neuroscience at the University of Cape Town in South Africa. He has a wonderfully weird background in machine learning, neuroscience, and psychology. Chris is fascinated by how we think and learn using both biological and artificial networks to explore intelligence. And with that, Chris, I'm going to hand over to you.
Sure. Let me start sharing my screen. Here we go. Okay, just want to highlight the screen that I've shared. There we go. Great. Great. Thank you so much for having me here. It's a real honor, especially in these tough times. Fortunately, I work from home anyway. And the way I'm going to stay sane to keep my mind is to talk about the mind. So this talk is about blind spots in computer vision, how neuroscience can guide AI, and a little bit about myself to go through. So I really love neuroscience and AI, but my main focus has been neuroscience. So I ran a few summer schools, so the Computational Neuroscience Summer School, then Derby X's each year. I've been at UCT, I've been to Oxford, I've gone to the Technical University of Berlin, and I have some consulting businesses on the side when I need some extra cash. But I'm not very important for this talk. The content is, so let me start with a warning, which is never a good sign to go with the talk, but some warnings. As you probably know, machine learning is hard. Having said that, I mean, brains are pretty much impossible, right? So it's biology. Biology, we have no clue what's going on most of the time. And so we just make a whole bunch of guesses. Having said that, there are plenty of things we do know. The final warning is that we're in lockdown, so I imagine it can be quite tough in these scenarios. It's not quite as engaging as in an in-person event, so please feel free to ask questions, and I'll do my best to frantically Google behind my computer to get the answer. Right, so in machine learning, when people say this is what the brain does, there's a little caveat there because they normally mean a very specific portion of the brain, known as the cortex. And this is a rat brain, the one that I've highlighted here. I'm also doing mouse, there we go. This is a rat brain. We're not talking about the cortex, which is very, very thin. And so it's about 1.44 millimeters. And then it's only a 2,600 centimeter squared surface area. And if we take about 1 millimeter cubed from this out of it, it weighs 10 to the minus 3 grams. Now, I mentioned this to contrast it to a computer and highlight the power of the brain. So in the brain, we have, in just 1 cubic millimeter of cortex, we have 50,000 neurons, but each neuron has 1,000 connections. So that means there are 50 million connections, and with 4 kilometers of axons, which are paths to connect them. In contrast, computer with 1 millimeter squared of CPU, the latest that I could find has 36 million transistors, but only 2 connections per transistor. And so the wiring is quite low. So it seems like the CPU wins in this regard, but if we scale this up, the whole brain, which only weighs about 1.5 kilograms, has 10 to the 11 neurons, 10 to the 14 connections, 8 million kilometers of axons, and it only uses 20 watts of energy to run this whole thing. We do a CPU, 10 to the 10 transistors, that's what I could find, but only double that in connections, and only 36 kilometers of wiring. And if we scale this up to the brain, it uses megawatts of energy. So there's a fundamental disconnect between these two scenarios. And of course, we're designing machine learning to run on CPU, GPUs. GPUs are very similar to these numbers, same order of magnitude. So you don't have to worry about the difference there. But there's clearly a fundamental difference. And I think that's one important reason why you should care about what the brain does. But some other important reasons why should we care about the brain is if you wanted to solve a problem, you can think about it in 2 fundamental ways, top-down or bottom-up way to approach this, right? So top-down way to approach a problem would be to say, okay, like what's the conceptualization of this problem? How do we do object detection? That's the computational aspect, okay? Then how would we solve this now that we have this problem? How would we implement this somehow, abstracted? Doesn't matter how we actually put it together. And so maybe you do like little nodes or neurons. Okay, Godwill says you can't hear anything. Can anyone else not, well, can you hear me? Put a thumbs up if you can hear me. Okay, great, thanks. I'm not sure what's wrong with his audio there, but I will continue then. Dramatic pause. Okay. So it's, for example, take a whole bunch of nodes, connect them up, and this could be a potential solution to solve object detection. Now, how would we implement this? Maybe if we're a machine learner, we would put in a Keras, we put in Python, we put in CPU. If we wanted to be fun, we could go on like a GPU or something else. The point is, there's plenty of ways to implement it. And one way to implement it would be in the brain, because clearly we are able to detect objects. So it's been done there. We're just maybe not sure exactly how, but we have good ideas. The other approach was to be bottom up. So given that we know a lot about how object detection is done in the brain, what are the algorithmic principles of how the brain implements it, and then work up from there. I hope that kind of makes sense, but the point is what we're doing is we're focusing on the implementation in the brain, and that is hopefully why you would care about it in the first place, because hopefully it gives us some insight into algorithmic solutions. Another important question is, has the brain been useful before? And this would be a very short talk if it hasn't, so let me move on from there. So it's important what the brain does, because evolution may have solved the functional problem already, regardless of what, well, not regardless, but with the plenty of problems out there that we're trying to solve with machine learning, and also like what the brain does, maybe it's been done already in our brain. However, having said this, it's obviously developed under different constraints. We were energy constrained, whereas machine learning, we just like throw GPUs as if we throw a whole bunch of stuff, scale it up, and hopefully it works, and then we go back. Obviously, I exaggerate, but that's the point. Okay, brain's also a very good starting point or source of inspiration if we're stuck in an issue and want to see possible ways to solve it. Look at biology, maybe it's done it before. However, having said all that, the brain is super hard to study. And so people have spent thousands and thousands of man hours, well, millions probably, in order to find clever ways to understand the brain. Because the brain really is the OG, the original black box algorithm, right? No clue what it's been doing. Okay, some assumptions for the audience is you have hopefully coded a neural network. You know what CNN stands for. You know the answer to the Monty Hall problem. Please add into the comments, what do you think the answer is to the Monty Hall problem? Do you stay or do you switch? And you must love machine learning for this talk. However, you should love neuroscience. Of course, I expect everyone to have coded a spike sorting algorithm, and that you can point out the lateral geniculate nucleus in any brain that I give to you. I hope this all makes sense. Obviously, I'm kidding. I'm also going to relax this constraint and say you hopefully are interested in neuroscience. But this is a neuroscience talk for people who know machine learning. Okay, this is going to be the outline of the talk. I realize it might be a bit long. Fortunately, we all remote. I can't tell if you're not paying attention. Feel free to fall asleep, go get some coffee, whatever. Okay, so we're going to go with inputs, processing, outputs, and then like a whole bunch of future areas that neither the brain nor machine learning know how to solve. Okay, let's start with the first one. Let's go like the input to an algorithm, to the brain, to machine learning algorithm. Let's focus on that. Now, let's start with the brain and let's look at the eye. This is how we input information to our brain. And it's going to be very complicated, but I'd like you to write down in the comments, how many light-dependent processes do you think you are for the eye? Okay, and then obviously I can't give anyone a prize, but you will know. So I'm going to run through the quick processing that goes on. It's not important, and then the answer will be revealed at the end. So just to highlight that it's super complicated, and there's a lot of things going on, even at the very early stages. Okay. Answer, how many light-dependent processes do we have to see is 1. We have a single light-dependent process, and everything else is downstream from that. which is crazy to think about. Yes, Lan, you were the closest with 3. Okay. So I suppose not many people ask this, but I love asking these weird questions. It's like, what do eyes even get us anywhere, right? Like, is that all that's necessary to actually see anything? And obviously the answer is no, but they are useful. So we get information from the outside world. They convert light to some sort of brain messaging, electrical signals. We also have some basic processing already at the level of the eye, and sometimes 2 eyes are better than 1, hopefully most of the time. But actually, like, seeing is relatively easy to replicate, and relative to the rest of vision, of course. So anyone has any ideas about what we can learn about the brain from an artificial eye, please feel free to comment or ask a question, and I can give you some insight there later. But yeah, I mean, we can learn a lot about how the brain is working by just building a process that converts light into electrical signals as well, which is also awesome. Okay, so here's some tips about how to improve your input. So check your data, provide continuous input, give it some experience, and maybe use some unlabeled data. I'm going to go through each of these. Let's go. Okay, let's start with check your data, and I mean, we have to talk about IMAGENET because it's a computer vision talk. So let's have some context, and I love XKCD, so I thought I'd add in this comic here. And for those whose resolution is a little bit low, it says when a user takes a photo, the app should check whether they're in a national park, and the person's like, yeah, sure, this is easy, it takes a few hours, easy to code, and also check whether the photo is of a bird. Now, this was many years ago, but it was estimated it would take a research team in 5 years. Now it's actually relatively easy to do. This would also take a few hours to implement with off-the-shelf. But to explain the difference between these two things is actually incredibly tough. So it's important to formulate these. Anyway, so it's also important to remember that when you do a test on ImageNet, a whole bunch of images and classify them, it's relative to human performance that people often do. And this was achieved at the end of 2014 by these people here in this paper. So yeah, it was about that time. And in this, you can see different architectures. I think this is when neural networks were starting to be used. Now, having said that, I want to test your knowledge on ImageNet. So I'm going to show 3 images here, which the state of the art, not state of the art, the one that in the previous paper in end of 2014 correctly classified. Put down what you think each image is. So what do you think this image here is showing? Type what you think. Okay. What about this image? Moth. Amazing. For those who've said dog, can you do a more accurate type of dog? And then finally, I think one of my favorite images in ImageNet. This is true. What is in this image? Man, these answers are so great. Okay, I'm going to reveal all the answers now. So ImageNet would say horse cart, wagon, I suppose it's probably right. So obviously, yeah, GT is ground truth, and then these are the top 5 predictions, with the orange one being correct. Whoever got Commodore, I'd be highly impressed. I hadn't heard of that type of dog before. So, I mean, if you think about people comparing these algorithms are smarter than their 5-year-old or are dumber than a 5-year-old, I've never known a 5-year-old to know what type of dog that is. And then finally, this is sunscreen apparently, which definitely would have been not my first guess. I'm going to do a similar thing, except now these are ones that the network got wrong. So please, 1, 2, 3, what do you think these 3 are showing here? This gives me a chance to take a sip. Okay, great. These are great answers. So I'm going to share the answers now, and the ground truth is what the labelers put. Okay. So the labelers put spotlight, spotlight, restaurant. Now the algorithm is run relative to what humans labeled this for these scenarios. So it's always important to remember that even if you got 95%, maybe there's some wiggle room there, and you should be more concerned if your network is getting 99.8% or something very, very high, because now it's kind of overfitting to these wrong answers as well. I realize it's actually a more recently updated IMAGENET with some extra cleaning, extra annotations, but the point is this is still a classic data set that people still compare their algorithms to that has clearly flaws if you just investigate a little bit. And I mean, this was in their paper. So you don't even have to go through the data set yourself. You can just read the original paper for those who want to. Okay. Let's move on to the next one about continuous input. So what I'm going to do here is I'm going to change one thing in this image, and it's going to be separated by a black screen. And I'm going to do the same thing again, except in continuous fashion. Okay, so something changed in this image. If you can spot it, you can say it. I'm going to do it again. I'm going to make it disappear. Did you see what happened? Back. Disappeared. Robbie, you can't just say yes. I don't know. Yeah, Brad. So, did you see it now when I did it continuously? There, there, there. It's significantly easier when there wasn't a black blank screen separating it. And the reason is we've been programmed this way. We expect the world to be continuous. And what we should learn from this, very simply, is to detect change, use context to understand change. Okay, so don't just classify on a single frame. And in order to do this, you can use a CNN and an RNN, or something called a 2+1D CNN for video, which is slightly conceptually, it's conceptually more difficult, but it's way more efficient to have a 2.1D CNN than a 3D CNN. But that's for, you can check out the papers at the bottom. And you can even fill in the blanks, so do some interpolation to make this a little bit better. But I think it illustrates the point that humans are pretty good at continuous change, and CNNs can learn a lot from that. The next one is we can improve our input just by experience, and is in using prior knowledge on your inputs. So, for example, with curriculum learning, if you start with data that's easy and end with data that's more difficult, the network seems to have a higher test accuracy. Having said that, this specific case is quite low anyway. I mean, it's all relative. But the point is that this seems to be a good way to go. And you can think about it, you don't start in grade 1 learning calculus. You build your way up. And I think applying this to your data sets and applying it to feeding the data set to your network is also relevant. Then transfer learning, which I'm sure many of you have implemented, is leveraging existing features and fine-tune differences rather than starting from scratch again, can definitely improve your network's performance and at least time. And finally, sample weighting, changing the importance of your samples based on their difficulty of classification or even how often they come up, because it's very unlikely you'll see a unicorn, but I mean, I think most children understand what they are. Having said that, all these aspects, there's something to think about, and that is, I'm not sure if you can see, but it says, how does this bias your network? Whenever you change your inputs, I don't think we can eliminate bias, but it's always important to think about. Finally, I'm going to quickly go through unlabeled data, and that is, if you think about it, most of the world is unsupervised. Some even think like supervised learning is a subset of reinforcement learning. Having said that, there obviously are circumstances where you do get supervised learning. But in order to get data from an unsupervised world for a supervised algorithm, we need to have some labeling. But this requires a lot of quantity, expertise to label correctly, especially if it's medical imaging, for example, a lot of time for the more complex you want to go. So if you just want to detect what's in an image, it's very easy for a person to write down modified person, slightly harder to do points, boxes, and segmentation. So it takes 78 seconds to annotate this image or this image to that. And so you can imagine if you want a more accurate data set, it's going to take longer to get there. So is there a way to leverage more unsupervised methods or semi-supervised methods like we do more in the world? I mean, humans don't need supervision, which I illustrate in this image here that maybe we do need a lot of supervision, even as adults. And it's important to think about, you need to keep learning as in life. Your network needs to keep learning. A, because you may encounter new things, and B, there's a scenario where it's something called concept shift, where your testing accuracy in the real world is slowly going to change to be less good just over time, as the real distribution of data in the world is not quite what you fed it in the first place. And so updating it to a more accurate distribution, or an updated distribution even, with some forgetting, can be beneficial. Also apply some semi-supervised methods where train your data with labeled data. Thanks, Jamal. Yeah, we do some labeled data, but there's also a whole bunch of unlabeled data which you were too lazy to label. Totally fine. Sorry, efficient. Let's say efficient. And so you get the network to then label this data with what it thinks, maybe around a whole bunch of them, but with what it thinks, and then train again and train again and train again. And this actually seems to have a better response than having purely labeled data, which is crazy to think about. But it could be because of like the number of data points you now have and some other important points. Point is, you don't need to label everything to have a network to learn quite well. You can leverage what it has learned. And then finally, active learning. So that's keeping humans in the loop. When your model isn't doing too well, ask a human what they think it is, or a few humans, preferably, as you saw in IMAGENET. And then get the right answer, and then tell the AI this is what the answer should have been, and get it to learn. Again, keep learning. Okay, I've obviously quickly gone through the input. Fortunately, in the digital setting, you can replay this video again. So feel free to do that and ask me questions at the end if anything is too difficult or I went through it too quickly. So I'm just going to go quickly through how convolutional neural networks see as well. And the answer is filters. Okay, so this is Terre Mountain for those who are in Cape Town. And we can apply a grid of numbers to up or down the essentially, I'm not going to go through filters in depth. I assume you know most of it, but it's okay. But here are a whole bunch of different filters, and it's important to know that this is essentially what CNNs use, and these are the features they use. And how these features chosen in a machine learning scenario, traditionally, if you just talk about machine learning, these features are extracted, as in like the top sobel, for example, or blur, and then you use classification and move on from there. Now, deep learning abstracts a little bit of that, and you don't need to do manual feature extraction, and instead this is learned as well. Something to think about is like, here are some examples. This machine learning is basically manually doing trial and error, and deep learning is just still trial and error, but it's automated. It's a great way to think about it. How are these features chosen in the brain? How do we decide if a feature is important or not? So here's also another question for the audience. Are these learned? Do we have to learn to recognize faces, or are we born with it? Okay, so on answering the thing. So for faces, are we learnt or is it innate? Patterns and edges. Which ones do you think? Okay, some good answers. Weirdly, people have tested this in cats quite crudely. And so what they did is they reared a cat in an environment where there were only vertical stripes. They did another one with only horizontal stripes, but in this case, they did only with vertical stripes. And what they saw is that this detection, they pretty much couldn't see horizontal stripes. They didn't have an edge detector for horizontal, only for vertical. And this uses a principle of the brain, pretty much called like colloquially, use it or lose it. So if it's not being used, just like throw it out. We're not using any of this inbuilt machinery to recognize horizontal stripes, so we're just going to use that part for something else. Which I think is interesting because now it shows that edges are actually learned to an extent as well, which is crazy to think about. Same with faces. Obviously, a whole bunch of asterisks, accuracies to everything I say, but I think that's just to swap this around quickly for use it and lose it is what happens if you lose it? Can you still use it? So if you lesion a part actually of the eye and that part of the brain never receives input anymore from that eye, what happens? And this is where they've mapped the eye. What happens is actually 2 months later, it gets filled in. So most of the brain area that wasn't receiving input now does receive input. So the brain uses pretty much most, like when people say we only use 10% of our brain, that's completely false. Pretty much use all of it. And it's large part due to neuroplasticity. Okay. So that was inputs in a nutshell. There's plenty more to go through, but yeah, if you have any questions, please use the ask a question at the bottom. And yeah, we'll address that afterwards. Okay, next up is processing. So first question is, how does the brain process information? Now, I hope you can see that there's a number in this image because it's a colorblind test. So if you can't see that there's a number, either the resolution is really bad, which is totally fine, or you may need to get an eye test. In any case, how does it go from this and convert it into something that we know? So the number in this image is 97, and the brain uses magic to figure it out, of course, because most of the brain, we don't know what's going on. Okay, but having said that, all distills down to the neuron, which we can think about as receiving input over here, and then projecting input to downstream neurons over there. And then, so we input, we sum it up, we get some spikes. Thanks, Sebastian. Through some spikes, and then pass the information on. Now, a lot of people like conflate these two and be like, well, this is a neuron in the brain, this is a neuron in a neural network. They're clearly inspired by each other because there's a weighting, there's some nonlinearity, and then we pass it on downstream. And of course, there's a lot of inspiration. Having said that, it's been shown that a neuron is more like a multi-layer neural network or two-layer neural network. So it's not quite as simple to conflate the two, but that's at least it served as a good source of inspiration. Having said that, we also quickly go to talk about receptive fields, and that is the area downstream that is influenced by a stimulus upstream of it. Yeah, so if light goes through onto the back of the eye, this is our little part of the light. This is our area of the brain that's going to be shining on. Is it activated or inactivated, and in what way? So an example here, we're going to have the light shining on this red area here. This is known as the receptive field, and the red part where it likes it, and the gray part where it doesn't like it. And so if we put the light on the red part where it does like it, these are activations, these are spikes. So the brain likes this area. However, if we move the light to an area where this part of the brain doesn't like it, then when the stimulus is on, there's actually no firing. And when the stimulus is off, there is firing. And we can think about receptive fields in the brain as very similar to feature maps or receptive fields in neural networks. So they definitely have inspirations between the two. And it's important to note that these receptive fields exist at multiple levels of the hierarchy, as in neural networks. So while brains may like certain orientations of a bar of light, so here it really likes these orientations and less so these orientations. It's built up all because of these lower level processes at lower levels of the brain. So it goes from this to this and keeps building up. And I'm going to abstract even further. So this goes from edges to more complex shapes, etc., etc. And this like just keeps building up and combines in interesting ways. And so here we go into the visual pathway in the brain. So light goes in, goes to the LGN. Yes, that is, you can now point out the lateral geniculate nucleus. One assumption reached. And then goes V1, V2. No one cares about V3, and in V4 in IT. And this is the what pathway, and this is the where pathway. But it's important to note that everything pretty much in the brain is a hierarchy. And obviously you don't need to know all these details, but what's happening is what, where, hierarchy, and there's a whole bunch going on to facilitate this information to keep going. So we go from dendrites to neurons, layers, columns, circuits, networks, areas of the brain, and then the brain itself. And it's interesting to know, I mean, maybe it's arbitrary that we decide to store this down this way, but each way we investigate these different levels of the hierarchy seems to influence our understanding of the brain in its entirety. And so it's interesting to notice that a lot of neural networks just ignore a whole bunch of aspects going on. Obviously, complexity is an issue, but this is a scenario nonetheless. Okay, so enough neuroscience for now. Let's go to some machine learning. So if we talk about like the what pathway, what I mentioned there, that's if you think about just image classification, what is in the image? Is there a boat? Is there a person? Cool. And then there's object detection. Where are they? Where's the boat? Where's the person? So answer, what do you think is in this image? What is in this image? Okay, I think milk chocolate dreamscape is the best answer. Thanks. But the answer I was looking for is horses. I was wondering how many you could count, which is non-trivial. It's not easy to count the horses. But what you employed there, even in a relatively difficult scenario, is you could detect them and you could probably know where they were automatically. And we use a bunch of processes to go on to influence where it is. Okay, so we have low to high level processing. And this is actually relatively easy for computer vision. And we have solved it for many years now. But if you really want to understand an object, what a horse is, it's slightly more complicated because we need some context. There's definitely attention involved, the way we're looking. We're keeping a memory store of what we've seen in the past, our entire past, how far, and in the image itself, and some sort of abstraction to the concept. And if we think about like moving from an instance of an object to an abstract version of it to get a representation, it just keeps going even higher. So categorical linking, to do this, we need more data. To do image linking, we need data augmentation. Maybe for these examples here, natural language processing, memory, add in a whole bunch of stuff to the network. Maybe that works. No clue how we would solve associative linking and a neural network. But maybe it's also just more data, more augmentation. Maybe that will solve it. But there's plenty more going on there to understand an object than to just detect it. And it's important to think about probing networks to determine its understanding. Of course, how you would do that is also an area of interest. But it's beyond just, is it there? And yeah, it provides a lot of insight. Speaking of abstraction, there's also more recent work with capture networks because they're aiming to do reverse graphics. So it's also in that vein. But we're not going to talk a lot about capture networks. There's a whole bunch of stuff still to be done there, but it's an interesting insight. And it uses a lot of principles of neuroscience as well. But I imagine the audience is mostly familiar with CNNs. So that's what most of the talk is and has been about. Okay. Computer vision. Let's talk about state of the art. A lot of people famously think it started in 1966 as a summer project. It's obviously more complicated than that. But it's nice to know that Seymour Papert was actually a South African at MIT. And so there's a history of computer vision, not only at MIT, but from South Africans doing a lot of work there. And I think we can continue that. So how good is state of the art in computer vision at the moment? Pretty freaking good, right? So here we can not only detect that there are people, but their pose and a mapping of their surface area of how we think everything is going on, which is incredible to think about. Just a few years ago, we only just surpassed human performance on IMAGENET. So we've gone a long way in a short period of time. Having said that, obviously there's still some things we're missing. And here's some state-of-the-art algorithms. And I'm impressed if you've heard of all of these, because some I think people just make up. And if you look on Twitter, you're not always sure, is this a new network or some other thing? Okay. Again, I'm going to do a similar thing with this network as what I did with the eye, just to illustrate there's a whole bunch of complexity going on. And for this talk, the details aren't super important. And if you do think you'd like to know more, you can go research it, but that's not what this talk is about. Yeah, here's what a mask RCNN does. And an RCNN is a region-based CNN, so we understand different bits of it identified. And we need a backbone architecture, we need a feature pyramid network, a region proposal network, region of interest. And what this does is it starts to classify more and more accurately, not only what's in it, but where people are in it. And I've applied it to this image here. And it's interesting to note that only the bottom, very small part of the image is actually detected, and the rest of it is ignored from the algorithm. And it shows that this network hasn't really been trained on, at least in this case, cityscapes. And so there's always going to be a limitation based on the data set that you've used. I would say that the mask RCNN also uses a lot of inspiration from the brain, because the feature pyramid network, the region proposal network, which I briefly mentioned, uses a single process for two parallel streams of not only what something is, but also where it is. And the brain definitely has a lot of connections. When I just had those two pathways, there's connections between those as well. So no matter what I say, it's always more complicated than that. Okay, so this state of the art in computer vision scales super well. So I just threw something together, detects a truck, detects a car. You can download the network and apply it yourself on some sort of video. Having said that, definitely has some issues. Detects this region as an umbrella. It's probably not true. And hopefully we get some improvement. Okay, state of the art. If you're looking at state of the art, I'm sure everyone here at some point has worked on BGG, okay, BGGNet. So where is this in state of the art? And why do we love BGG? It didn't even win the competition. Everyone seems to have used it. And I think we love it because it's orderly and repeatable, so we can understand it. It's easy to visualize, it's deep. So that's why I think we love BGG. There's more complexity in there. Then ResNet and DenseNet, which is a large success. So if we think about what a standard connectivity of a network would be, ResNet adds in the skip or residual connections, and this seems to do improve performance. And so they've scaled it up to like 152 layers, which they decided 152 and not 153, because more than that, in testing, the GPU ran out of memory. So it's relatively arbitrary that they stopped at 152. Then the more recent one is DenseNet, where instead of just doing one, you have a whole bunch of connections. And this provides more input backwards in training of the network and more input forwards in processing once you have an established network. You can also think about this kind of like intuition. If you know the answer, you don't need to think about it a lot. You can just skip a whole bunch of scenarios and get to the answer right away. And maybe do some checking. But I think it uses some of those principles as well. Highway connections are also another term that people sometimes use to think about this. In any case, these use the same like backbone architecture, or can use the same backbone architecture. So these connections were added to solve the vanishing gradient problem, so that, I'm sure we know, but it's to make sure that the error propagating backwards through the network doesn't go to zero, and then you don't know what the true error is. These connections make that it's still accessible in very, very deep networks. Now, the brain has these connections too, but it doesn't use backpropagation. So I'm not sure the brain has a vanishing gradient problem per se. It has sorts of other problems, but it has these connections for additional reasons. Some other networks that are really awesome and more recent. So IMAGENET is where we have a neural architecture search or automatic machine learning, or we use an evolutionary algorithm to determine the optimal neural network to solve a specific problem. Now, as I say, it's clever computation, but it's normally for a specific task. And there can be parallels to evolution. And you think about this as like learning how to learn. And this clearly has used some, again, evolutionary insights from there. Okay. Another recent state-of-the-art network is known as EfficientNet, and the insight was, instead of making a network either deeper or wider, do it in a proportional manner. And that seems to have a really, really good performance for not many parameters. So in this graph here, I have X as the number of parameters in millions, and Y as the IMAGENET top 1% accuracy. And the IMAGENET, which is an AutoML algorithm, has like one of the highest accuracies, not the highest, one of the highest, but definitely the highest number of parameters. Whereas EfficientNet has significantly fewer parameters, but has the best performance. And what this kind of shows is that more parameters is not equals more performance. And this should make sense if you think about the brain in other creatures, because elephants have more neurons than we do, and whales have bigger neurons than we do. But we would argue that neither are actually smarter. Okay. So quickly to end off the section of processing, the brain has also led to neural networks with skip connections, feedback connections, lateral connections together. Talk about dynamic processing. So lateral connections are like often to other neurons in the same layer or even on itself. That'd be feedback. Skip connections we mentioned, then also saccades and foveation. So those are attention mechanisms to focus on specific regions of a network for processing. And then people have also been doing spikes in neural networks. And this adds an extra like intrinsic time component to the processing. And these are just examples of looking at a spiking convolutional neural network. So some inspiration from the brain, but still very different. So normally spiking neural networks have better performance, but sometimes they're only tested on MNIST. There's a recent paper where they have managed to correct some of the issues there and scale it up onto like IMAGENET and CFAR, but there's still a whole bunch of like asterisk C's to these numbers. The final thing brains are definitely inspired is the nonlinear function, where while ReLU is super quick and you can train a large network with it, leaky ReLUs seem to perform quite well, and having this negative portion is definitely a benefit, at least to some extent. And in the brain, we have positive input and negative input, as in exciting neurons, inhibitory neurons. So it's not just a matter of scaling your positive. There's also this negative aspect, and this adds quite interesting properties to what a brain can do or what networks can do. Okay. Again, I've gone through this very quickly. Please ask questions. Obviously, I think Darby's going to just ask all the questions. That's fine. Cool. So if we go on to outputs, over here we have two subsections. The first one's going to be CNN visualization. So how would you visualize a convolutional neural network? Another one is looking at brains using CNN, which kind of flips the title on the head. Instead of using neuroscience to look at AI, we can use AI to look at neuroscience or related aspects there. So, of course, it's an online talk and you can skip things you don't like. I'm going to go through both. So the first one is CNN visualizations. And so we're just going to rub out the other one for now. So we're going to ask and answer 4 different aspects of this visualization. And the first one is like, what is the output after each layer? Second, what feature does each layer extract? Then how would you visualize areas of interest? And finally, ask the network to generate something. Okay, so the first one is an activation. So let's look at the activations of VGG. Again, it's great to visualize. That's why we love it. If you give it this image of a cat, we give it at different layers in the network, we can see that it goes from edges to more complex characteristics with blobs and more complete features. Over here, the blank bits are because they're running dropout during the stage, and so that's why they're blank there. But you can see the progression of the features of the activation maps moving up. In a related term, what do you see in this image? What is this? What is this? Obviously, you're going to say dog and a cat. Please identify what type of dog. Please identify what type of cat. I'd be impressed. So if we process this through a convolutional neural network, we can look at these activations in 2 different aspects, I suppose. You can, given all these neurons and these many different layers in different channels, because it is wide and it is deep, you can view it through different aspects. And if we go through this is a spatial activation. We can see different channels that are activated in different layers. And conversely, if we go through the different channels, we can see how the spatial mapping differs according to different areas of interest. So over here, it's way more fine-grained, and over here, it's very coarse. And these features kind of pick up like some features of a nose, some features of, looks like a squirrel, but hopefully still the text as a cat. But yeah, you can look at the activation maps like that. Then if we look at the features, you can also, you can go through the network and ask what features do you like the most for each neuron, each channel, etc. And you can get A, insight, and B, pretty patterns. And please do this because it's relatively easy to do. I can't remember how many lines of code this is, but it's quite small and it allows you to visualize what's going on. Hopefully this makes it a little bit more interpretable as well. A third way to understand a convolutional neural network is through heat maps. So over here, there's a paper that looked at different images and then they occluded it. And depending on the occlusion, they wanted to test, did it get the true label correct and what aspects of the image were important to get to this label. And the Pomeranian, what this blue aspect here shows that if you occlude the face, it gets it wrong. But interestingly, for a car wheel, the numbers were actually important to understand this as the true label. Now, maybe it needs more than just a picture of a wheel to understand that it's part of a car and context matters. But it's interesting nonetheless to note that these can be the cases in what you would think is an obvious example of a wheel. Starts to pick up like an 8 in letters and some relatively arbitrary things that you wouldn't intuitively think about it unless you actually probed it further. So this is definitely an interesting way to look at computer vision. Relatedly, you can also go through different layers of network and visualize the heat maps there. So in this case, I'm going to go through each layer and you'll see where the concentration, where the features detected, because obviously this detected it as elephants or elephant, and where did it use to pick it up. So those are edges, these are more blobs, these are more concepts, and so you can see that the regions where it's picking up that to determine that this is an image of elephants. Then the fourth one would type to visualize CNN. This may not be exhaustive, is generation. So, I mean, this is, I think, StyleGAN. You add two different images. So this would be the source image. This would be just style image, Vincent van Gogh, combine the two and generates it. That would be an example, like, a generation of an image. You can also ask the network to go crazy and be like, just keep going. And this is Google's deep dream. Keep going with your features. If you pick up a feature, just add it to the image. Just like go wild. And then you get these weird effects that keep going. And this can actually lead to insights to how the network's working. Like what feature is it looking at? Where does it pick up? What does it weight? Another example. None of these spaces are real, but you can see how different weightings of them can influence what the image generates. And there's also a cool website you can go to play around with GANs, which may be intuitive and not always easy to work with. And so here you can actually work with them quite quickly and easily. But yeah, none of these spaces are real. That's not important. Okay, now the reason I bring these four specific ones up is because neuroscientists have been doing this for quite a while. However, obviously with different techniques. Okay, so this is the reason why sometimes these visualizations are known as in silico electrophysiology or virtual brain analytics. It's because it's obviously using inspiration from the brain. So here we can actually put like electrodes onto individual neurons and determine what's happening at different layers in the brain. We can look at connectivity patterns, the types of neurons that are there, the properties of learning that's going on in that scenario. We can understand a lot about what's going on by recording neurons while they're being exposed to a stimulus. Relatedly, you can do, this is again very similar, record from monkey, give it different images and see how neurons in that area respond to. So these are the features that it responds to really nicely, or in this case, the hand, not so much, whereas a face, a lot, occluded face, not so much, etc. And this they're recording this part of it. Then we talk about like heat maps, and in this case, it's similar to saccades, where you ask and measure a person to identify what's in the image. And here they followed the tracking of the eyes, and they found that the eyes jumped around a whole bunch, first of all. And secondly, it picked up like key aspects of it. And then if you convert this into brain space, this is how it kind of represents these different concepts in relation to each other while processing. And this is similar to what's happening in a heat map visualization of a scene. Then in terms of generation, we've been doing this for ages. You ask a person, like, draw an image, you can see what concept they derive from. So here I've given an example of people with two different types of problems in their brain. So here they're given this image or this image, and then they're asked to either draw it or to do a verbal identification of it. So here, they cannot draw what's happening at all. They can identify what's going on, which is somewhat weird. We normally conflate the two. And then over here, they can draw the model, but they can't say what it is, which is also super weird. And the important thing to think about in terms of the brain is that everything is seamless until something goes wrong. We hardly notice how complex it is. And these two scenarios are known as apperceptive agnosia and associative agnosia with these two different issues. But we can determine a lot of the cause by asking a person to draw or to identify, to generate what they see. Just ask them. Okay. We're going to quickly go through looking at brains using CNNs as well, because the brain, again, is the original black box analysis. So with a whole bunch of inputs going in, we use this many neurons. Outputs are normally muscle. These many neurons, 10 to the 6. Processing uses 10 to the 11. Also to note, there are more than 5 senses. There are more than 5 senses. So in this case, you can use machine learning to look at medical images, look at experimental data, look at brain activity. And we can use this machine learning for diagnosis, analysis, or interpretation, or mix them around with all the different combinations. Basically, we can use machine learning for a lot about how to understand the brain. In the first case, for medical imaging, they have a MRI image, and we can detect different aspects there and see what's wrong. Are normally tumors, because those are the most overt. But they're starting to be stretched a little bit further to like cognitivity patterns and more than just nothingness or issues in the brain itself. Interestingly, they use a lot of MRIs use like 2.5D instead of 3D images, which actually makes things simpler in CNNs. You can also use it to skip a very complex process that takes normally minutes or hours. In a traditional computer programming setting to generate a nice image. You can teach a CNN to generate it from the raw data, skip that very intensive process, and generate the image much, much quicker, so it encapsulates that portion of it. Maybe you want to like double check a few, but it encapsulates that portion of it. Then the issue with medical images is the data isn't readily available in large quantities, and it's also important to know what ground truth is. If you say someone has a psychiatric deficit, like why is that the case? How do we know that is the case? And it's normally a phenotypic response rather than a brain and anatomical issue there. Anyway, it's very difficult. Okay, then in terms of the experimental data, people have used the ResNet to do some pose detection, and this speeds up the science and how you would more accurately track behavior of mice, rats. This is also a rat. They use it for monkeys too, and flies. So this just speeds up experimental data analysis. Not too exciting. More exciting is brain activity using machine learning there. And very complex image, very now important. There's spike sorting. Essentially, it's like how do you determine where in the brain the specific signal was from when it's very noisy. So there's a lot of signal processing going on, and using a CNN to do pattern matching essentially makes this process significantly quicker if you have thousands of neurons that you're recording on for long periods of time. Yeah, there's a few methods that use CNNs. Killer sorts, I think, is the latest top of the range at the moment. Related to brain activity as well, people have started using machine learning to generate a face based on brain activity. Yeah, so patients are shown faces, and then just by reading brain activity, they can generate what they think the patient is seeing, which is crazy accurate, because this is what it was in 2011, which is still pretty good. And then now in 2017, they're using it to generate very, very accurate scenarios there. Yeah, I'm not going to speak about in depth because this is also like super complicated, but highly interesting. In terms of understanding the brain itself, there's a classic paper from 1996 which started doing these edge detections, pan detections from just by natural stimuli, and then recording from, I think they use monkeys in this scenario as well. And building up from that is some people made a neocognitron. This is after that, the HMax, which used a lot of principles of what we knew about the visual system to move further. And then Jan Currin actually directly used that for his first Linnet to determine the postage. Okay, then AlexNet has been directly applied to understand what's going on in the brain to some extent. Again, more complicated than that. And hierarchical CNNs have been interestingly applied to the brain network hierarchy in the visual system, monkeys and an artificial neural network at the same time, and to show a lot of similarity and a lot of insight, such that if you show a monkey and a network the same image, the network can predict the activity of the neurons in the brain, which is crazy to think about. Interestingly, this wasn't trained through backprop. They use way more complicated training methods for the actual activity of the neurons. But the point is, there's a lot of really interesting work being done there. Yeah, and then you get a whole bunch of different types of networks that have been explored and expanded upon in order to try to reach a scenario where we have artificial neural networks that are very similar in terms of behavioral detail, biological detail, but are way more explainable. So instead of just substituting the brain for another black box, we hope to actually do it for something that we can explain significantly better. Okay. That's that, and now we're going to go quickly through some problems that are still prevalent in vision in general. So computer vision, neuroscience, etc. So let's talk about some problems and future directions. And this is a relatively quick section. So for all the data collected and theories developed about the visual system, why couldn't neuroscientists make a functioning visual system? Now, it should be alarming in that it signifies we were missing something crucial. Having said that, we can now say that our intuitions about the visual systems were largely right. We were just missing the power and the data in order to scale it up. But there's also been some recent machine learning papers about just basically scale everything up and it just works. Obviously, asterisks. But it's crazy to think about that was all we were missing as neuroscientists. This is computing power, in any case. How does another important question and problem is the brain encode representations, and can computer vision capture concepts? So here's an example where the neuroscientists recorded from neurons. So high graphs or lots of ticks means that there's a lot of brain activity going on, means it likes it. So here are pictures of Mark Hamill. Then the name Luke Skywalker is shown as an image. Then Luke Skywalker spoken in a male voice, and Luke Skywalker spoken in a female voice. And these neurons seem to really like this concept, regardless of whether the input was an image of the face, image of the text, or sound. Again, Yoda also seems to do surprisingly well. But this shows that the brain encodes representations. Now, having said that, we're still not entirely sure how. There's some arguments about whether it's sparse or distributed. It's a whole minefield of awesome research as well. Point is brain represents concepts. Another thing, faces. Faces are an interesting area of study that we tend to focus on and find a lot of faults with. None of these faces are real, but we would all detect them as faces. Similarly, this, I'm sure many of you will automatically recognize as a cat face. Even though portions are on, we know it's art, and it's not quite a real cat face, but understanding the concept, the representation of the cat face is there. By running this through Google state-of-the-art algorithms, it detects as blue art, visual arts. I mean, cat doesn't even appear here. So we can understand the concept beyond just what's represented to us, just from face. If anyone knows what it is, if you have an issue with recognizing faces, answer away. Max pooling is also another issue that Jeff Hinton has highlighted, and he doesn't like seeing ends working so well because it means they'll be very hard to get rid of with these capsular networks. And it's interesting to note that brains do average pooling most of the time, not all the time, most of the time. And so this represents, like, ask you a question here, like what's in the image? The normal CNN will probably recognize this as a face. We know that's not a face. What about now? Probably a CNN and a capsule network would recognize this as a face. We would know that it looks like a face, but it still isn't actually a face. We've never seen eyes that look like that. We've never seen a tongue that looks like that. We've never seen a nose that looks like that. But we understand the concept of it. Relatedly, there's something wrong with the space. I'm just going to tell you the answer quickly for time, and that is it's symmetrical. We probably knew something was wrong, but we couldn't quite understand what it was. And so we pick up issues at a high level before exploring it in lower levels. Another issue is invariance. Now, so let me just vary this quickly. You move the eye there, you move the mouth there, still detects it as a person. Now, the solution to this is normally solved by data augmentation, or capsule networks aim for equivariance through routing so that this relative portions or locations are still maintained and get a better accuracy. And if you flip this image completely upside down, it gets the correct answer of coal black color. Yeah. What's in this image? It probably took slightly longer than you expected to recognize that this is the map of the world, but just the right side, I mean, just upside down. That's what I meant. With South Africa being all the way at the top of the map, or near the top of the map. It's just a different perspective, but even humans have trouble with this variation of something that we normally expect to be represented in a different way. It does take slightly longer to process. So I'm not sure if this is explicitly a direct issue with machine learning, because humans have this problem of variance as well. We do expect things to be a certain way. Also, another problem we shouldn't forget about is memory. So in networks, we normally encode memory in the weights. We sometimes have external memory, and we typically have consistent learning rates. Obviously, people experiment with that. In the brain, we have synaptic connections. We have distributed memory, episodic memory, so specific instances, which may have high valence, and with that, emotional encoding. We can have multi-sensory integration of information, and we have a salient learning rate, which definitely gets modulated depending on how much coffee we've had that day. Of course, in the brain, there are dynamics on many, many timescales. I'm going to show you one example here, where what's in this image, it probably just looks like a mess of black. But if I show you this primer, and then this image again, you can probably see that face in it now. And it's because we have some feedback at very long distances in the brain, which inform what we should be looking at in this image in order to inform and infer what's in there, which is interesting. Context is important as well. So in this case, these two gradients look somewhat different. And then in this case, they look much different. But I mean, this is just explanation for why, if you want to go through it again. But these two are the same, and these two are the same, but the differences between them look remarkably different. And it's because of relative proportions, or relativeness, and what we infer from the scene. Where is light coming from? Where do we expect things to go? And that informs a lot of illusions. One of my favorite illusions is the dress. So white and gold and black and blue, and it depends on where you infer the light source, essentially. And so even if you know the correct answer, and the correct answer is black and blue, for me, I still only see white and gold, even though I know the true answer. So why is that the case? So when I see something like this, where we see adversarial attacks on artificial neural networks, I'm like, well, optical illusions are like that in humans too, and we may not be immune to them. Okay, how many colors? I saw someone asked in the questions 4 currents, and so I'm going to answer it here. So in this image, we have 16 million colors, but normally with only 3 currents, we can only see up to 10 million colors. And this, in the brain, we have a high receptivity to green. So we see a larger proportion of green relative to other colors. And so you should go see art in person, because printing doesn't have that same proportion of green. It blurs it out a little bit. And yeah, so you should go see in person. And with 4 currents, a person can see up to 100 million colors. So hopefully that question's been answered. Okay, another question is of time. How quickly do we need to determine something? In machine learning, we often want to do this as quickly as possible. But even in the brain, this can take hundreds of milliseconds to really determine what's going on. Some reflexes can be quick, like 200 milliseconds. Others take orders of magnitude longer. And so timing is still an issue. Neuroscientists also have, normally just say V1 in the brain, the first portion of the brain that does visual processing. It's mainly just for edges and spatial frequency. But of course, the brain is complicated, it's biology. There's slightly more than that. It also happens to be involved in motor activity and thinking in general, logical decision making, and significantly more. And so it's very dynamic, very diverse. Noise is important. Humans respond much better to noise than neural networks do. And so we can probably learn a lot about what's going on in the brain for how to account for noise, to inform how to augment and change on neural networks a little bit further to improve their performance. Texture, computer vision algorithms often overly rely on texture to determine what's true and what's false. And do we really understand how the brain solves object recognition? Well, no, I'm nearly done, I promise. So what we do currently understand is the crux of the problem, which is invariance, the issues that result from this demand, where the brain solves it, what's capable of supporting this recognition, and the fundamental units to facilitate this. So why haven't we solved object recognition in the brain or in computer vision? So the problem is we must fortify intermediate levels of abstraction, and this algorithmic solution lives in a very, very large space of detail. We lack a systematic operational definition of success, and there must be more synergy, essentially. Okay, with that, there's plenty more that neuroscience can add to beyond just what I've spoken about just in computer vision. But I'm going to end on a quote that says, "There's no scientific study more vital to man than a study of its own brain. Its entire view of the universe depends upon it." With that, thank you very much. Thanks, Nerve, for having me. And please stay safe and stay healthy. And now, questions.
Thanks, Chris. This was really, really great. I think I can speak on everyone's behalf when I say this was very fascinating indeed. So yes, thank you for being our first speaker. And I think with the time running out, we have time perhaps for one question. So I'm now going to invite maybe 1 or 2. We can see how it goes. I'm going to invite Siobhan back on stage just to ask the questions on our attendees' behalf. Okay. Siobhan, are you with us? Okay, it seems like her video might be hanging. So I'll ask the questions, and then we can. Okay, so let's see. The first top voted question is from Ben, and he is asking, self-supervised learning or self-supervision is a relatively recent learning technique in machine learning, where the training data is autonomously or automatically labeled. It is still supervised learning, but the data sets do not need to be manually labeled by the human. But they can, for example, be labeled by finding and exploiting the relations or correlations between different input signals. What are your thoughts on this? Yes, and then he just asked us to ask.
Okay, cool. Yeah, thanks for a good question. Yeah, semi-supervised learning is really, really awesome. And you do need at least some initial data for that training. And hopefully it's relatively easy data in terms of like curriculum learning in order to start the labeling of it. I think it's a fantastic effort that we need to understand more about why it works so well. We know quite a bit already, but there's a whole bunch about why knowing some can lead to knowing more. Yeah, my initial insight from it is that having some guess and then iterating upon that is better than just not guessing whatsoever. And feeding back what you think is true in order to facilitate your speed of training and your accuracy of training. Having said that, I still would love to know more about what the biases that this inputs into the system as well. If it gets one or a few labels continuously run and feeds that back onto itself, I wonder how much further this goes and whether it stays in the system, as it were, beyond that. But yes, in semi-supervised learning, I think there's going to be a lot more coming out of that. And as we realize, the brain is mostly unsupervised, but there is definitely some supervision. I think this balance is going to should be exploited more and more in understanding neural networks.
Okay, perfect. Siobhan, I'm going to throw it to you to ask one more question.
Thanks. So I'm going to ask a vicious question. Can you comment on how the brain learns, how it contrasts with what backprop does, and whether there are any insights we can apply to neural networks?
Yeah. Yeah. Backprop is frustratingly good for neurosciences because it is very accurate and very targeted. And it's like, this neuron, you were this neuron. You need to change by this amount. And there's no level of specific targeting in the brain that does that. Having said that, there was a relatively old paper now, I think it was 2014, 2015, called by Tim Lillicrap on feedback alignment, where you don't need to know the exact weights going backwards. They can be fixed, and you can still learn what's going on. So you don't need backprop for a neural network to learn what's happening. It just is normally much better. There's also a way more recent paper that Tim also authored, I think in February, which I still need to read, where just using local learning rules, you can have learning systems in the local learning rules in machine learning and artificial neural network. It can be as accurate or more accurate than a backprop system. So you don't need a direct targeted specific feedback signal from a lower system in order to get this high accuracy. And the brain has a lot of different learning mechanisms going on, different learning rates, and different learning styles. Or sometimes if it gets a lot of inputs that it likes, it will increase in weight, sometimes it will decrease, sometimes it will spread out, or diffuse, it will have more connections, it will have stronger connections. You also have to think about how it maintains these connections. So it's always weighing up like learning and memory versus the amount of energy it costs to keep this going on. Yeah, in essence, the brain is complicated. But yeah, thanks for the question, Avishka.
Okay, great. I think we do have to wrap up now. So on that note, I'm going to hand over to Siobhan to just sort of close it up for us.
Yes, thank you, Chris. That was a really amazing start to Nerve Online. And if everyone can please give a virtual round of applause to Chris. And also please take a second to vote on our poll so we can give Chris some constructive feedback. And then just last minute housekeeping, please remember to follow our page. This is on Crowdcast, you can follow Nerve. And then you will all have received a survey. We'd really appreciate some feedback, so please take a moment to complete that. And then finally, one more thank you to Chris. And we'd also like to thank our sponsors, Stellenbosch University and the Biomedical Engineering Research Group, which is based at Stellenbosch. We are very glad for this opportunity. And then we will be in touch soon to let you know about our next event, which will be on the 22nd of April. Same time, same place.
Okay, awesome. Thank you, everyone.
Thank you so much.
Bye. Bye.